All right, gang. Math 6610, sampling distributions. I see this as kind of the bridge between probability and inference. And let me give you something to tattoo to the brain. Uh, in statistics, we explore the dynamics of relationship between samples and population. Population is just the entire group of subjects, elements, dogs, cats, trees, people, ACT scores, gestation periods, whatever it may be, that we are studying. And a sample, and for us, we usually work with a convenience sample, but we hope in theory to work with a random sample. Is just a subset of the larger population. Now, if we start with the sample and work in the direction of the population, we call this inference or inferential statistics. And what you can think about in this direction is that the random sample is known, but the population value that we're interested in is unknown. So, what percentage of prospective voters intend to vote for a particular candidate, maybe in 2024? Well, I don't know that, and you don't either, and neither does anyone else. Well, we want to estimate the unknown. What we will do is go out and take a random sample, use inference techniques to make an estimate of the population mean, proportion, difference in means, whatever we may be studying. Now, this direction is different because we start with a population that is known and we have an unknown random sample. Well, we call this probability, right? So, for example, if I have a population, let's say it's 3 cards. I have an ace and a king and a queen. Well, what is the probability of getting for example, an ace? Well, we know it's 1/3 because we know the population from which we're drawing. To calculate a probability, we have to know the population from which we draw. And using laws of probability, we can determine the likelihood of getting a particular random sample from it. Now, most of this class will be spent examining inference techniques, everything from 1 sample t-test to 2 sample t-test, pooled and unpooled. We get into ANOVA techniques. We'll get into non-parametric. We'll get into MANOVA, logistic. A lot of different inference techniques. But I think we need to pump the brakes a little bit and take a look at this direction. Now, I'm not going to teach you probability in this class. I assume coming into a Master's of Mathematics program that you have a fundamental knowledge of basic laws of probability. But what I want to do is I want to lay the foundation or the framework for these inference techniques. Now, let me pump the brakes a little bit and tell you what I know is going to happen. Most of you, some of you at least, are going to check out on me here. And you're going to say, well, I already know sampling distributions. I already know the central limit theorem. I already know all this stuff. I tell you, when I go out into high schools and I observed high school teachers teaching statistics, whether it's a high school level or an AP course or even a dual credit, I'm not overly impressed by the way they present the central limit theorem. It shows me that they can read the definition out of a book, but they really don't know what it means. So the purpose of this video is to dive into the weeds and really think about what's going on with the central limit theorem, because any of us can state it, right? The central limit theorem states that if you have a population with mean mu, standard deviation sigma, take sufficiently large random samples from the population with replacement, then the distribution of means will be approximately normally distributed. Very true. But what does that mean in the broader sense of sampling distributions? For example, let me just get the cart in front of the horse here. We are going to, if you take Math 5500 from me, we're going to get into matrix operations. We're going to get into variance covariance structure of our errors. So we're going to look at the variance matrix of the errors. So we end up with a, an n by n matrix. What does that particular element mean? Well, it's the variance of the errors. Well, what does that really mean? Well, guys, it circles all the way back to this thing that we call sampling distribution. So the implications of this video are extreme in you truly understanding what goes on behind the scenes when we have this distribution, this sampling distribution, and we're able to calculate these things called p-values and calculate confidence intervals to make estimations. It all goes back to the central limit theorem. So, I hope you'll slow down. Excuse me. Get a cup of coffee here. I hope you'll slow down and give me an opportunity to teach you something here. Now, what happens? First of all, we begin with a population, and just as the formal definition says, we start with a population that has mean mu and standard deviation sigma given, all right? Now, the next thing we do is we start talking about this taking sufficiently large random samples. Well, it turns out that if we have a normal distribution, if this distribution here with mean, mu, sigma, standard deviation, sigma known, that this distribution can be normally distributed or not normally distributed. If it's normally distributed, we have the luxury of working with sample sizes 2 or larger. Again, up here, sample means critical, because to get a mean, we need 2 or more people, 2 or more observations. If we don't have a normal distribution, then we typically talk about large random samples as being 30 or larger. Now, what we really mean is 100 or larger, but things work out pretty nicely around 30. So if this happens, and again, this is a big if. So we have mean and sigma known. We either have a normal distribution or we don't. If we set our sample size, again, up here it says population with replacement, right? So we set our sample size at 2 or larger, or 30 or larger if we don't have a normal distribution. If all of this is true, this is what happens. So let me give you an illustration. Let's just say that we're working with a distribution that is not normally distributed. So this tells me that I have to have a sample size bigger than 30. So let's just say, just for the illustration here, that the sample size is 42. So what happens is I dive into my population right here. I pull out 42 observations, and I take the sample mean of those 42. The key to really understanding the sampling distribution central limit theorem phenomena is to realize that my attention shifts from taking one at a time. So I have the first person, the second person, the third person, the fourth person. But I look at these 42 collectively, and I give them a collective score from the sample mean. And I use X bar because it's a sample mean compared to mu, which is the population mean. Well, I throw these 42 back in the mix, again, with replacement. And then I sample 42 different, well, I take another sample of 42. There could be some intersection there. And what do I get? I get the second sample mean. Do it again. Throw the 42 back in, close your eyes, take 42 randomly selected people, calculate their sample mean, and I get the third sample mean. Now, imagine doing this forever. Now, you can't because it would be academic exercise that you would never complete. But in theory, imagine doing that forever. Well, what you're going to have is you're going to have a whole bunch of sample means. And we give this whole bunch of sample means a name. It's called the distribution of sample means. X bar. Now, kick in the central limit theorem. Central limit theorem tells us that this distribution of sample means will have three characteristics. They will be normally distributed, or in other words, be a normal distribution. So if you were to put these values in a calculator, again, you can't do it because there'd be forever, right? There'd be infinitely many. But if, in theory, you could put this into these numbers into technology and click the histogram button, the histogram would form a perfect normal distribution. Well, a normal distribution is defined by two things, right? Its center and its spread. The central limit theorem tells us that the mean of these sample means, now a lot of means going on here, right? The population mean is mu, the sample mean is x bar. If we could add this number plus this number plus this number, all these numbers, and divide by a very, very, very large number, we would get a population mean of the distribution of sample means. This is going to be equal to the value that we started with way back here. The next thing is the shape. I'm sorry, the spread. The standard deviation of the sample means, which we call the standard error, is going to be sigma over the square root of n. So again, it's this value divided by the n. So in my demonstration here, this would be sigma over the square root of 42, because as the illustration I just set at 42. And again, we call this the standard error. This thing back here is called the standard deviation. Once we divide by the square root of n and get into the distribution of sample means, in this case, this measure of variance, this measure of variation, if you will, is called the standard error. Now, what does this allow us to do? We know that, let's say there's an example that house prices in a large city are positively skewed with a mean price of 500,000 and a standard deviation of 50,000. We take a random sample of n equal 12 houses. What is the probability that the mean price of the 12 houses exceeds $490,000. Well, we go back to the central limit theorem, right? Central limit theorem says we start out with a mean and a standard deviation. We have that. It's 500,000. Standard deviation is 50,000. We either have a normal distribution or we don't. In this illustration, we do not, so we need a sample size of 30 or larger for all of this stuff that I just demonstrated to you for it to take effect. But we don't have that, right? So in other words, we can't determine this probability because this distribution of sample means won't be normally distributed. We have all, in R, in our graphing calculator, we have these normal distribution calculators. We don't have a positively skewed distribution calculator. So guys, as the way this stands, we can't do this problem. Now, what if we upped our sample size to 50? Well, then we've got something that we can work with. First of all, if we're taking houses out at 50 at a time, we know that the first sample mean and the second sample mean and the third sample mean, all of these means, again, forever, we'll have a distribution that is normally distributed, that will have a mean equal to the population mean, 500,000, and then it'll have a standard error equal to sigma divided by the square root of our sample size. What did I say, 50? Yeah. A lot of fives there, right? So whatever this turns out to be, we can put it in our calculator easily. And as long as I didn't miss anything, it's about approximately 7071. All right, so let's go back to this problem. We now can do this. So what we want is 490,000, which would be right about here somewhere. And we want the area, what do we say, exceeds? So we want this area right here. Now that's really easy to do in R. Let me bring R up and I'll show you how to do this. So R has a normal calculator and we call it P norm. Now what happens is the value that I put in first. Now let me pump the brakes a little bit. This may be the first time you've seen this. P norm in R has 3 entries. First of all, it's the value at which you want to calculate the probability from a normal distribution. The second is the mean of the normal distribution. And the next entry is the standard deviation. Now, what this gives by default is it gives below. So if I put 490,000 right there, it's going to give me the area below. Well, gang, we know that the area under the normal distribution is equal to 1 square unit. So all I have to do is take 1 and subtract this area below to get the area above, right? So simple stuff. So I need to come in and first of all go ahead and put 1 minus. So I need the 490,000. The mean was 500,000. And the standard deviation was 50,000 divided by the square root of 50. So the likelihood of getting 50 houses that have a mean price of 490,000 or higher is, well, the probability would be 0.92, right at 0.92. So let's circle back. I want to end this video really quickly, but let's circle back to something you will run into in 5500. And as I talked about earlier, 5500 we get into regression, so we'll get into something called the variance of the errors. So we'll have an error. Let's say we have 7 terms. Our variance matrix will look like a 7 by 7. So for the third unit, for the third case, we will come in and we'll get a value. And let's just say it's 0.07, you know, whatever it may be. What does this tell us? This tells us that for the sampling distribution of the errors, and again, I'll teach this in detail in 5500, but I just want to give you an illustration where understanding, give me the opportunity to teach you the central limit theorem is going to pay huge dividends, not only in 6610 and 6620, but 5500, 6500, and probably even probability from time to time. So this particular thing, this gives me the variance of the errors. And I've had students reach out to me before and say, Dr. Darber, wait a minute. We only got one error for that particular case. Yes, but we have to realize that there's this underlying sampling distribution that does have a variance for this particular error. So again, there's broad-reaching implications on having just a very solid, firm, thorough understanding of sampling distributions, because eventually we're going to get into hypothesis testing, and I'm going to illustrate that probably in the next video. Unless we truly understand the underlying probability distribution from which we calculate our p-value, then we really don't, I think, truly understand the statistical decisions that we're actually making. All right, gang, that's all I got.